Greetings and welcome, friends. Today we are learning a completely new parent function that we're going to deal with. We're talking about absolute value, and you might remember my friends were just telling me that absolute value will take a number and make it positive. So absolute value graphs. Here we are. It says an absolute value function is a function that contains an absolute value expression. That makes sense. And the parent absolute value function is f of x equals abs x. All right? And this is what the absolute value function looks like. Now, if I just had f of x equals x, that would have been a line like so, right? With a slope of 1. But when I absolute value it, it's all like, oh, no, you didn't. I can't be negative. And it ignores all of these points and then teleports them to be positive versions of themselves, right? And as a result, the absolute value graph ends up having this V in it, which I think is great because there's like a V in absolute value. Yes. And so that's what it looks like. It's symmetric about the y-axis. What does that mean, symmetric? Does anyone know? Symmetric means that it's a mirror image of itself, that these points over here you could mirror over there, right? And it's symmetric over the y-axis, all right? So that's what that means by symmetric. It's a mirror image. And it says the following, that the vertex is the point, and my vertex is going to be kind of like my y-intercept was with lines. It's my starting point. All right, start here if we can. Which we might do that more tomorrow, thinking about it in terms of that. So the vertex is the point where the graph changes direction. Notice it's going down and then is going up, change in direction. So the vertex of the graph of the parent function is always going to be 0, 0. Now how about this, domain and range? What was domain again? It's been a while. Domain are the possible x values. Possible x values. So for domain, if I was to take this entire graph and smoosh it down to the x-axis, it would exist everywhere, right? The entire x-axis would be covered in the corpse blood of an absolute value graph. I'm so sorry that I crushed you. I didn't realize you were there, absolute value. Oh, man. Right? That the entire graph would be covered, right? And that's why the domain is all real numbers. It's everything. It's from negative infinity through positive infinity. And the range is the possible y values. And if I was to smush this to the y-axis, if I was to crush this horizontally with my awesome Hulk strength that I have and am known for, actually that's the first thing people think about when they hear the name Waddy, Brian. They're all like, oh yeah, that strong guy? And they're like, wow. And if I smushed this graph, notice it would only get smushed to these points, right? And it would go up forever, so it would get smushed all there, but it wouldn't have any values that were negative. So the range is only positives and 0 are the possible y values. Question, comment? Okay. All right, let's check this out. Now, if I want to think about graphing each according to like a transformation, all right, adding a k, this is going to be a vertical shift up 3, right? And subtracting a 2 when it's on the inside is going to be a horizontal, exactly like we did in previous lessons, shift. And instead of left 2, which you would have expected, horizontal is always sneaky. It jukes you, right? It jumps in the other direction. Instead of a negative 2 on the x-axis, it's actually going to shift towards the positive 2 direction. So it's going to shift right 2 units. So let's graph the parent function. So my parent function for the absolute value has a vertex at 0. And watch this. This is how I graph it. It's up 1 over 1. Up 1 over 1, up 1 over 1. It's got a slope of 1 on the right side. And for the left side, it actually has a slope of negative 1. So I could go up 1, backwards 1, up 1, backwards 1, and I could graph that graph. And you don't have to graph it with a ruler or nothing, but I figure I've got this straight edge here. All right. And so my parent function looks like this. Parent function. And then all the chillins are going to be the ones that I get as a result of transforming this parent function. So a vertical shift up 3, that means this point at 0 gets shifted where? Up to 0, 3. This point at 1, 1 is going to get shifted up 3 to 1, 4. This gets shifted up 3. And every point is just going to get shifted up 3. So even these ones over here. Up 3 and up 3. Right? And so my new graph is going to have a vertex that's been shifted up 3. And every other point has been shifted up 3. Now, question, has this changed the slope of my absolute value graph? Is my graph steeper? No, it's still up 1 over 1, up 1 over 1, or up 1 backwards 1, up 1 backwards 1. So it hasn't changed the slope. It hasn't changed the shape of this. It's just changed where it is. Okay, so that's what that would end up looking like. Let's do this one real quick. So I'm going to graph this one way faster. Vertex is at the origin, up 1 over 1, up 1 over 1. Right, and it's the classic parent graph you guys should become super familiar with today. All right, is like that, and like this, and like that, and like this. And right, there's the parent graph of the absolute value function. And this one is experiencing a horizontal shift by -2, which means it's shifting in the opposite direction, which is going to be right 2. So my vertex is now over 2. This point's over 2 to the right, over 2, over 2, over 2. And these points are over 2. Actually, that point hits the other point, which is weird, where it used to be. Right? And everybody just gets shifted. Does this change the slope of my absolute value graph? No, it's parallel to the original, right? It's not any steeper. It just changes where it is. It was a horizontal translation. Right? So where's the vertex on this graph? Where's the vertex? Yeah, the vertex is right here. So the vertex is at 2, 0. Where was the vertex on this graph? That was 0, 3. All right. And they asked us the domain and range. Oh, dear. Oh, boy. So much to cover. Trying to help you guys out, though. All right. So question, for the domain of the purple graph, it's still everything. Shifting it up still covers all the x values. If I smushed that down, it would hit everything. So domain, you could say, is all real numbers if you want. And what about the range? What are the possible y values? If I smush this all to the y-axis, it would be everything from 3 and up, right? For the purple graph's range. So I'm going to call that the set of all y such that y is bigger than or equal to 3. So it did actually change the range of the parent function. Right? All right, how about domain for this purple one? What are the x values? Did they get changed when I shifted it over? All right, is negative infinity plus 2 different? Is positive infinity plus 2 different? Nah. If I smush that graph down, it's going to cover the entire x-axis. So the domain is the same, all real numbers. Yeah? And how about the range? If I smushed this to the y-axis, what y values would get hit? Well, everything bigger than or equal to 0. So actually, it kept the range of the parent function in this case. So I'd say the set of y such that y is greater than or equal to 0. Wow. Sneaky stuff. All right, let's try Example 2, and that's all I got to get through today. We're going to have a part 1, part 2 of this lesson. All right, example dose. Example 2. All right, now check this. Let's graph the parent. Where do I start to graph the parent function, absolute value of x? Start at the origin, up 1 over 1, up 1 over 1, up 1 over 1. Right? And so the slope is 1 and -1. I describe these as slopes. I think it's a helpful tool for us to think about these absolute value graphs. So there's my parent function. And what does multiplying the outside by 2, what is that going to do? Well, it's not a shift. It is going to be vertical, though. It's a vertical stretch by 2. All right? So this point at 0, what's 0 times 2? 0. What's 1 times 2? 2. What's 2 times 2? 4. What's 3 times 2? 6. 4 times 2. 4 times 2 is 8. Yeah. And then, right, this one, yeah, it's a mirror. It's symmetric. Remember we talked about that. So all of these points are going to be the same things, just mirrored. So when I graph the outcome, did it get steeper? Yeah. I had to make this steeper. In fact, I might even say it's twice as steep. I think that would be a wonderfully accurate way to describe its steepness. All right? And side note, pro tip, what is the slope of the purple graph? Back up. What's the slope of the purple graph? It's going up 2 over 1, up 2 over 1, up 2 over 1. Yeah, so that's actually an interesting outcome, that the slope is now this. So the slopes are +2 and -2. You could think about it like that. All right. Didn't change the vertex. It actually didn't change the domain or range there either. All right, what is this going to do, do you think? It's outside. Going to be vertical. It's less than 1. It's between, right, 0, 1-ish. So it's going to be a smush amity, right, by a half. And then what does this minus sign do, do you think? It's going to flip it. Flip over the x-axis. It's a vertical flip or reflection. So let's see. Let's graph our parent. Origin, up 1 over 1, up 1 over 1, and up 1, backwards 1. Hopefully you guys just like, my goal for you today would that be you would like lock the idea of a plain old absolute value graph in your head, right? The classic V, that you would be solid on that and graphing through transformation. So here's our parent function. So this blue graph you could have memorized here. All right. Yeah, sure. Absolutely. Yep. Aha. So a half. All right. Let's pick something that's divisible by 2. So here's a y coordinate of 2. What's half of 2? 1. And this is -1/2, so this is actually going to be at -1. Okay? All right, so this point is now at -1. All right, here's 4. What's 4 divided by 2? 2, and then make it negative. -2. Because of the minus sign. Yep. Let's see, what's another even number? 6. Here's 6. What's 6 divided by 2? 3, and make it negative. -3. Let's try one of these ones over here. Here's this point, which still has a y-intercept of 2. What's 2 divided by 2? 1, and make it negative, so that's down here. Let's see, what's this point? 4 divided by 2 is 2, and make it negative. And so perhaps you guys can kind of see what this graph is looking like. Amity, you seeing this? Excellent, excellent. All right, so this is now an upside down absolute value graph. And let me ask you this question, friends. What is the slope of this purple graph? From its vertex, it's going down 1 over 2, down 1 over 2. The slope is, yeah, -0.5 for this part, and it's going up 1 over 2 for this one. And yeah, so this number out front for vertical shifts or stretches or smooshes is literally going to end up being the slope of your line in the end. Okay, so that's like a super great way to think about it. And so this one, the domain and range was the same. Domain for this purple graph is the same, all real numbers. Could someone tell me what the range is for the purple graph? The range, if I smooshed this to the y-axis, it would be everywhere. How would you describe these numbers on the y-axis? Everything 0 or less. So I'd say it's the set of all y such that y is less than or equal to 0. It's all the negatives and 0. All right, thank you for watching, mis amigos de internet. Bye-bye.